are expressing their happiness and they are requesting you to go at same pace, sir. They are able to follow.
Okay. Fine then. Thank you. They are able to follow. That's the most important, Kada.
Sir.
Good.
Sir, I am stop present so that you can share your slides.
Yeah. 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 Are you able to see my screen?
Yes, sir, it is visible, sir.
Okay, fine. So tell me when to start. I'm ready.
$30 are there, sir. Maybe we wait for another 3-4 minutes and we'll start.
Yeah, that's fine.
Okay. Sir, participants are asking your email ID. Shall I share it in chat box, sir?
Yeah.
Okay, sir.
అది ఒకటి హలో రెడ్డి గారు
Sir.
ప్లీజ్ షేర్ ది ఐఐటి మెయిల్.
ఐఐటి మెయిల్, sir. Okay, sir. Okay, sir.
అంటే ఇది ఆల్రెడీ లోడ్ అయిపోయింది.
సరే సార్. ఓకే సార్.
మీకు తెలుసు కదా
నా మెయిల్ బాక్స్ ఉండదు సార్.
ఎందుకు ఇట్ ఇస్ gvrao@iitgn.
ఒక నిమిషం సార్, టైప్ చేస్తాను.
gvrao@iitgn. .ac.in.
Okay, sir.
I'll repeat, gvrao@iitgn.ac. డాట్ ఇన్ ఇది స్టాండర్డ్ కదా మామూలుగా.
ఓకే సార్. Sir, maybe we'll start, sir. So, once you finish
Yeah.
your
Yeah.
finish your
My
call,
copy.
you can start, sir. No problem, sir.
Okay. Yeah, coffee will keep it away. Good morning, everyone. Namaskar. Vanakkam. Let us begin by quickly recapping what we have done in the yesterday's session. In the first part of it, we have reviewed what will be the outcome of the geotechnical investigation. In this, we gave importance to, I should say, three kinds of things. One was the standard penetration test. We have seen very quickly the limitations of this. I'm sure you must be aware of that. And but that is the only way in which we can assess the sandy soils. It was primarily meant for sandy soils, though whenever you have layered soils, that is maybe sandy, maybe clay and all, we will also do the testing continuously. And there are correlations available for obtaining the relationship between, let us say, the angle of intersection phi and also the relative density from the corrected values of SPD and values. We also have correlations, particularly for strength and other things for clay soils. But for clay soils, it is best done by actual sampling and laboratory testing. When you talk of laboratory testing, we find that there are many methods. Consolidation, of course, is standard now. All of you know about that. So I will not want to spend time now. We will spend time towards the end of this presentation today. And from strength viewpoint, we said there's a direct shear test, which is an excellent test because the box actually is a very thick box, so it gives confinement, something akin to a condition, which more or less represents the kind of condition we may have in the field also. And we also have tractional testing of three different kinds: the unconsolidated undrained test, then consolidated undrained test, and then consolidated drain test. The link which we also is sandy soils. We should, I must have mentioned yesterday also, the value of the phi we are going to get is going to be almost the same whether it's going to be a saturated sand or just clay sand. There's very little change in this. So the results are obvious anyway. The water does not have any influence on the properties of the sand itself, of the sand particles. It is also probably easy for us to get the required field density, if it is possible, in the direct shear test. If you want to conduct a tractional test on sand specimens, you have to make them in the laboratory, and it is quite a tough job. Essentially, we people do it for research purposes and not really for practice purposes. For practice, the direct shear test is quite relevant to us. I will also add that the angular friction which you are going to get from a tractional test on sand is going to be slightly lower than that by direct shear test, because our direct shear test gives a confinement more than the normal sigma 3. It is because equivalent to sigma 0 condition. And so when you are applying it, we should try to make corrections either way. We had also mentioned is about EU test or unconfined compression test. Both are similar. In the unconfined test, we don't have any confinement. In the EU test, we have confinement, but we do not allow any drainage, both in the first phase of application of confined pressure or sigma 3, and also in the second stage of application of deviator stress. In that case also, we are not going to allow any drainage to occur now. That's why it becomes undrained test. For a clay sample, in unconfined compression test is equivalent to EU test only with confinement 0. Now, this we have seen clearly, the illustration I have given to you, that gives us for a saturated clay sand, for a normally consolidated clay soil, what we are going to get now, we are going to get a horizontal granular, which means that the angle of friction is 0, very nearly 0, and then the value of C is there. This is an undrained condition.
Sir,
So we
excuse
call
me.
it as CU. Yeah.
Sir, is the
Yeah.
slides being changed, sir? We are not able to.
No, not yet. Not yet.
Yeah,
Not
yes,
yet.
sir. Okay, sir. Okay, sir. Thank you.
This is just recap. The slides are not changing.
Yes,
Are
yes,
you able
sir.
to see
Yes.
the second slide? Yeah.
Yeah,
I'm
now
not,
it is
as
changing,
of
sir.
now,
Yes,
I'm
sir.
reviewing what we have done because
Yes,
that
sir.
is
Yes, sir.
a-
Yes, yes, sir. Done,
yeah.
sir.
So
Thank you.
when you conduct a UC or EU test now, we are essentially going to get an angle of friction 0, nearly 0, and then we are going to get a quotient intercept. And because it is again EU kind of test now, and it's a quick test basically, there is a pore pressure generation, but then this is not dissipated. So what we are going to get is a CU, undrained value, and phi U value is there, but it's equal to 0. Then for a clay solve behavior, for the long-term behavior, we have to conduct a CD test or we have to conduct a CU bar test. So it means consolidated undrained test, wherein we also measure pore pressure. So the effective stress conditions, effective stress values of some parameters, C prime and phi prime, is what we're going to get by CU bar test or CD test now, which will definitely take long time, which will take longer time than other tests now. Now this becomes important for us when we are considering the capacity of clays now. When we are trying to assess the bearing capacity of clays for the so-called undrained condition, for the so-called immediate after construction, during or after construction, we are looking at undrained case only. That means we are looking at a total stress value of Cu only, phi being 0. If you are interested in the long-term condition, which is also going to be there, naturally, what we are going to look at, we are going to look at C prime and phi prime. That means effective stressing parameters are going to be used in the equations. So that means for clays now, we have two different sets of bearing capacity. One bearing capacity based on total stresses, bearing capacity equation based on total stresses. Another bearing capacity equation based upon effective stress. Effective stress is going to be everywhere effective stress. C prime, phi prime, gamma prime, everything is effective only. That means gamma prime is gamma so much. Okay, this is what we have to always remember. So for clays, we got like this. For sands, of course, we have to find out the what do you call effective unit weight, that is upper unit weight, wherever is relevant, wherever what table is there near the foundation, we have to look into that. The other thing I didn't define, of course, clearly right in the beginning is the very definition of shallow foundation. So we all know that the definition of shallow foundation by Terzaghi himself is that when the depth is going to be less than the width of the foundation, probably that is called a shallow foundation. That's his definition actually. But today we say that whenever the foundation is going to be immediately just beneath the surface, very near the surface, the load is right onto the soil. So we take it as shallow foundation. That means very clearly, even rafts are also going to be having the same kind of situation. Depth could be less and width is going to be very large. The other kind of thing is that when we are going to have a situation other than this, when it's going to be load transfer is not by directly transferring, but through, we said, the end friction and cone capacity and bearing capacity, it is going to be defoundation. That means when the soil near the surface is not suitable for our transfer of the loads, transfer of the column loads, naturally we are going for a deeper foundation. So I'll repeat again, where we're going to have load transfer immediately just below the foundation, direct transfer actually, that is what we call as a shallow foundation. And that means we should extend the argument of Terzaghi's definition of bearing capacity. So then I would like to draw your attention back to Terzaghi in trying to tell you two things now. One, of course, is the fact that One, of course, is the basic fact which I initially also, but worth looking at again, that we talked of this cone actually, this conical portion basically, or wedge portion, which is active wedge. You can say that now this line actually, this line from the horizontal is at phi. This line from this is going to be horizontally downward at phi. So that's how the wedge is defined. Other point also said was that the failure plane or failure zone doesn't extend beyond the foundation, bottom of the foundation. So it is only stopping here. So the effect of this is there, obviously it will be there. That's only as such charge only. That is what we have to keep in mind. The other part of it is also he has used actually for this inclination of these both these things. That means the linear part of it now defined at 45 minus 5 by 2 because that is the way in which the failure planes in passive condition. This is a passive wedge anyway. So that's why he defined as 45 minus 5 by 2, both these lines 45 minus 5 by 2. So that is the way in which it defined, and then this is assumed as parallel now. So this is what I assumed. We also got solutions for a rough foundation, smooth foundation. No, now of course by basics work also, the rough foundation is going to be giving us more bearing capacity. A smooth foundation is going to be giving us slightly less bearing capacity, slightly less. So once you get the result now in the Itazaki's format, standard format now. So this is original kind of course. You can say that what is most important for us is you see the change now, values of N gamma, NQ, and C. Now in the beginning, that means up till about say 15, 20 degrees, which are not realistic, very loose conditions. If you just go around 30, you can see 30 degrees, I mean, angle of friction now. We see that it's almost going up so high actually. The difference between angle is going very small, but the increase factor is going to be tremendous actually. So that is what is going most important. One is assessment of the the foundation soil condition is subsoil condition is going to be very as perfect because between 29, 30 and 30 and 31, 30 to 31, 32 degrees, there's going to be so much difference in the Bernoulli factor. You can see this is going up actually from here to here is moving up slightly. And here itself it says actually beyond this, because the curves are at up to 40 degrees only. For example, the N gamma values is representing phi is equal to 44, N gamma is 260 degrees, I mean 260 value, and phi is equal to 48 degrees, N gamma is 780. Just a mere change of 4 degrees, almost more than double, 2.5 times the value is getting now. So that is the kind of appreciation we have now in getting the correct assessment of the foundation soil conditions, subsoil conditions. And unless you do that correctly, naturally the values are going to get meaningless because most reports give us around 30 degrees now, and we don't know whether it's really 30 degrees. It's going to more than that. I can show you a lot of cases wherein we could have used higher values of friction or higher values of CN5 and get a tremendous increase much beyond what we think of factor of safety. For example, if the soil is 48 degrees and we put 44 only, by choosing a lower value of N gamma in this case, which is very critical in most cases, we are getting a factor of 2.5 automatically just for this gamma and gamma being or become N gamma because N gamma is going to be changing by 2.5 times almost. So this aspect we have to keep in mind always. That's why I thought I will emphasize it now. The other important factor which will come into our mind by common sense, which will be used later, is also coming out from the Itazaki's interpretation only. I don't know whether how many books are giving it, but I have picked it up from my old copy of Leonard's Foundation Engineering. So this on this axis, on the horizontal axis, we got the value of angle of friction phi, and then here this axis representing the vertical axis representing depth over B, D over B. So depth of the foundation over the width of the foundation is the total width. So what is it we are finding is that the influencing zone of influence actually is going to be up till B only for 30 degrees angle of friction. And then if it is going to be more, naturally it's going to increase now. And with the depth increasing more and more, or DOB increasing more now, this value is going up to 2. At 45 is becoming 2. That means what is really happening is the depth of influence zone is becoming larger and larger for higher angle of friction now. And that's why you remember that we are considering influence zone for capacity and also for our calculations. Also, what zone of influence? That zone of influence is coming from this basic theory. It could vary, say for 30 degrees angle soil, sand, we can say that about 1.5, 1.2 or something like that. It is actually moving to higher angles like this now, up till 2.5. So this value is about 2.5 roughly. So that is the zone of influence which we are going to get directly from this theory. It is, I should say, more easy for us to comprehend this other than getting that total burmester bulb and things like that, because this is showing you what is happening near the surface. The other point, of course, is what is the width of this zone now. I mean, if you recall my previous picture, it shows you that F is the value of the upheaval of the foundation soil onto the ground now. So that width of that is going to be taken as from each side F value. So that means on one side F and other side another F now. 2F is the zone of influence totally. So that is, and also giving like this now. For example, for 30 degrees now, this zone of influence is only, the zone of influence is, let us say, 3. That means the zone of influence of the soil which is participating in the low transmission through the passive wedge basically, or passive zone, is about 3 times the width actually. And then you can see that this moves further into, it's going up and up actually. So the more is angular friction now, the more soil participates, that's why the bearing capacity increases. So one should always insist that we have as much product value as possible. And if it is sandy soil, if by any chance we are going to densify it now, each angle of friction, each degree of angle of friction is going to make a lot of difference, not only in the bearing factors, but also in influence the zone which is improving the bearing capacity. I think that is a concept we should also understand. Tomorrow, when we talk of improvement of the ground now, this is zone we are always considering now. So both in terms of width, in terms of depth now, higher the angle, more zone influence. More zone influence means that much soil is participating in the load carrying capacity. In fact, we use it extensively when you go to payments also. When you put geosynchronous in payments now, we understand the importance of this very clearly. And so shallow foundations, one ought to know this zone of influence. Okay, this defines the zone of influence from a depth and width viewpoint. So then other thing I didn't show that picture to you in terms of basic, we defined initially the local shear failure, general shear failure, and the load deformation curves, load settlement curves, like a Plato test now. So when you got your general shear failure, we already seen the entire zone is influenced basically. The width is what we're talking of here actually, and the depth we are talking of this. And so we are likely to get something like this. The Plato test values is going to be definitely quite steep, and then maybe it will fail or it will go down slightly. And if you take off only local shear, you can see this. I was last time I showed you a picture wherein there is a dotted line here, dotted line here. Now here everything is dotted line actually. That means it's not going to form, but it will show some tendency. So that is local shear failure, in which the soil just below the foundation is going to participate in the load bearing. And so, as I already told you, the zone of influence is becoming lesser because it's punching down, is going down only without really moving the soil by the wedge on either side. It not allow us to fully form the passive wedge, which is going to be the zone of influence or which is shear zones. And that's why you can see this is simply coming down very fast compared to this now. So another way of look at it is, it will simply go down completely. It may form partially wedge now, it's simply going down. That means no soil around is going to be influenced. Very little influence. It's only the soil just below the foundation is going to influence now. Obviously, when the zone of influence is less now, or when the soil adjacent to the foundation and deeper also is not influenced, obviously. What's going to happen? The curve is going to be going steeper. That means failure is very imminent very quickly. This is what we call a punching shear actually. Of course, for our most of the conditions now, we combine both of them. That means both punching and local shear, sometimes very difficult to distinguish. So for our purposes, we combine both these things, punching and local shear failure. Weiss himself has defined what is this, where we should take this, where we should take, where we should take local, where we should general, where we should take punching. So his way of looking at it is, when you got the relative density of sand, that means very dense sand somewhere between 0.7 to 1, naturally, and the depth of foundation influence we already mentioned now. So this is a way in which you have long rectangular foundation. That means something like a stiff footing. So that is one of influence for this now. And also coming between around 0.35 relative density to this is going to be the rectangular foundations. Circular foundation, the difference are shown by dotted line. So that means above this line is shear failure, between these curves is going to be shear failure, and below this is going to be punching shear failure. And in fact, these values are also used in IS code indirectly in specifying how to take care of the local and local shear. Because in IS code, we are not doing the punching shear. In fact, quite a few researchers combine local and punching shear. So the point we are trying to mention is these two curves are defined, even the values are going to use in our equations for the IS code. So indirectly they don't say this, but the tabular form which I'm going to show today is going to give you that, okay, between this range of density for sand, we have to use the local general shear failure. If the values are low, then we are going to use local shear failure. If the values of density or relative density are somewhere in between, we are going to interpolate. So this is coming from this actually, from this basic data provided by basic as well as 1963. Then this I have already shown you. The picture was not clear last time, so I thought I will put a better slide basically, but it's worth going through. Tazagi's case is very, what Bowles recommends, of course, is best for very cohesive soils where D by B is less than or equal to 1, or for a quick estimate of Q ultimate. Mind you, quick estimate of Q ultimate to compare with other methods. Do not use for footings with moments under horizontal forces or for tilted bases or sloping ground. Mind you this. That means the original equation by Tarzagi, though there are corrections available, I mean, methods are available to take care of. For example, you got inclined load, obviously we say that take vertical part of it for bearing capacity. The horizontal part of it, we are going to assume that the whole foundation is going to move, and on the side of the foundation, we will have a passive pressure. Other side, we are going to activate pressure. So difference between these two are going to take care of the horizontal force, horizontal thrust. So like this, we can always modify the basic equation. But he recommends that don't use this basic equation. This is only for quick estimate. It just tells us what is the basic story. Okay. Then a lot of work has been done by Hansen, Meyerhoff, and West. We know that we can apply these series for any situation that applies depending upon user preference or familiarity with a particular method now. That means you continuously believe in something, you have particular experience on certain things, so then we can use any one of them now. And obviously, when the base is tilted, when the footing is on slope, only Hansen and Basic give you. And basically, the Hansen simple factors. Hansen has given extensive deliberations on the factors, shape and depth and inclination factors. And he has also given us for ready use the simplified factors of Hansen, which we are using today in our code. So this is something we have to keep in mind. Now, this table also I have shown you yesterday, but then I thought this is a more clear slide, but it's more easy for us to see everything. This is also a page taken from Bowles' book. Any one of you can see this in the foundation chapter now. Very important. What did I say? Is that Glovic has done the initial test on the kind of soils, that means on the 5, 6, 7, 8 tests actually, and then Moose has done on samples on the soils 1, 2, 3, 4. Now, what is the range of the properties we are using now? D is equal to this much, B, and then L, length of the foundation, gamma, phi, and C. So we see that the width is, the depth is varying basically up to about 0.5 maximum, from 0 to 0.5. The width is of course varying up to 1 meter, and length is varying maximum to 2 meters only. The gamma value, which is actually the test value, it can be anywhere between 15.69 to I think maximum is 17.65, and phi value from 37 degrees it is varying from 22, 25, 20 degrees, and in this case the C value which are getting is something like this. Okay, that means from 3.92 to almost 12.7. So what I wanted to tell you is that there is a range of these foundation values of D and depth of foundation, width of foundation, length of foundation, and there is a range of gamma, phi, and C within the limits. And what they did find out experimentally the ultimate bearing capacity values in terms of kilogram per centimeter square. And these values are given here, and the values by Moose are given here. And Bowles, in fact, he has modified these equations by his computer program in those days. Today, all of you can do it more easily by using any kind of software. And so what he has done is he compared what is the prediction coming for these properties, for these parameters, by Tarzagi, by Meyerhoff, by Hansen, basic. Ballasiri, we didn't really say much on this, but anyway, there's another theory which is also used by some researchers and some practitioners. So he compared 5 methods actually with the model test values. So now what is it we are going to get now? Suppose I take this now, 10.8 is the value, 10.8 times in square is the now the actual what do you call calculated value, predicted value is 9.4, 8.2, 7.2, 8.1, 14. In the other case also it is varying so very widely. Okay, so none of them are comparing with this now. So what did he say finally is, it's not seen very clearly here, but if we go back to the table, we'll say that we'll find out that out of the 8 tests now, 4 of them very clearly somewhat near Drasagis. That means 4 measured values, 4 test values are somewhere near Drasagis. And 2 values are near Hansen. And 1 each actually is for Basic and Bala. So what is it we are going to say? By statistics will say that Drasagis is better now or Hansen is bad. But then, as I said, Hansen gives you a wide range of situations. That means we got the depth factor, the shear factor, English factor. Then we got for inclined basis foundation. We got the slope now. And so that's why it becomes most general kind of situation. So that's why we are using the Terzaghi's mode of the basic equation, but then using the Hansen's values, Hansen's factors, because they are generalized for different issues. That is what we have to keep in mind. So with this background, which I given you, in comparing the results now by help of Bow's book, so we will go to IS 6403, which is our Bible for doing carrying out the estimation for bearing capacity. And what we should also remember is the reasons which went into the development of this code, which has been revised slightly here and there. But then one has to, when once one practices, we have to go for as per the codal provisions, whether it's national or international, depending upon the nature of the work and magnitude of the work. Now, we can always, for experience, but we have to always go through the provisions. And for a large project, if the provisions are not being methodically followed now, we should be able to also quickly realize why we are not necessarily following it. For example, for bearing for foundations on, let us say, backup soils, we may not be able to follow that. We'll have to use some other theories for this now. And also experience of certain kind of foundation, certain situations are going to be very good. So in those cases, in those states or in those projects, we may differ from this now. That is also permitted by the code. I think I have read this earlier to all of you. It's better to uh, again recap that also. And I hope that by now you would have downloaded the copy of IS 46403, which is freely downloadable from the BAS site. So what did the code say in the beginning itself, which normally people don't read. That's why I thought I will read it aloud for you. The bearing capacity foundations is needed for dimensioning the foundation for any structure. Several methods are available for the determination of bearing capacity of shallow foundations, and this standard gives some of the methods which are commonly used for the purpose. It doesn't say that this is the only way. Comparison of the results shows that when each of the various methods is applied to different problems, no one method consistently gives higher or lower values of allowable bearing pressure. The designer must therefore regard the methods as aids to design, which cannot replace the critical role of engineering judgment. In fact, some of you who are members of the Indian Geological Society, there is an IGS forum created, and a lot of practitioners are commenting, oh, this particular clause is wrong, or this clause is not understood, things like that now. But then, what they should also keep in mind is that the role of judgment, which is provided by the code itself, actually. And they have realized long back that the different theories give us different values now, and still we have to use the judgment part of it now. So interpretation is going to require, including the corrections or SPT test also. They're varied kind of thing. And I may draw your attention to again book by Bowles, wherein he says today around the world, not many are doing the corrections also. That's why I didn't spend much time on that. The war button correction, which you do for SPT, are also not done. But what is done, of course, are the corrections basically for the kind of equipment you are using for SPT, for the kind of energy we are going for SPT. So they actually, because this method is very popular throughout the world now, but people use different kind of hammers, maybe slightly different kind of method of dropping the hammer and things like this now. And with all these corrections are mentioned clearly for the method of dropping, for the friction here and there. And then they also corrected for an energy of 70 kilograms blow hammer basically. So that is done anyway, but not necessarily for war burden and also for deltency, because they say it's already taken into account now. And various people have studied this now. That's why sometimes we see that the test itself is what we now call as a non-standard SPT. We call it a standard penetration test, but because of the very many variations in the testing now, because inaccuracies we are doing in actual testing, and its misapplication, we call it also as a non-standard SPT test. But nevertheless now, because of the so many correlations which are there, because simple and easy, which I mentioned already, we continue to do this. We continue to do this. But when you use the correlations, we have to be quite mindful of what are the limitations of the correlations and what are the limitations of your own testing procedure, and are we corresponding to the energy which is given there now. Why I'm telling this again and again is that when I show you the correlations available for relative density as well as the angular friction, the table I have taken, this very clearly mentions that it is meant for energy of 70 kilograms of the hammer. That means the weight of the hammer is 70 kilograms. Ours is 0.5. So when you are not doing this, I mean, we don't have to use same hammer, but the correction available for converting the energy into right standard energy now. So unless you do the correction now, these tables are meaningless now. Okay, the other last point before we go ahead is about the utility of the plate load test. I will not, I have actually deliberately avoided considering plate load test because of plate limitations. The plate size is very small compared to actual foundations, so the depth of influence is not going to be affected by this. It gives a small depth of influence. It cannot undertake the effect of water table. It cannot really consider the large depths which will be there. For example, if I want to use the plate load test value for a wide foundation, the values are entirely inapplicable basically. So all the results which are going to come out of plate load test, I don't want to, I mean, normally it is what you say that outdated. So we depend upon SPT, DCPT, we rely upon testing and not really the way in which we do the plate load test basically. So it is more or less outdated. We do it in very rare circumstances. And one other reason people also have been doing it is that the designers, particularly when they use the STAD, they expect a modulus value also. This modulus value is also given as a correlation between the SPTN value and the correlation and the modulus. Now, this is also a table given provided by us by Bowles now. So I'm not saying that we should always depend upon Bowles only. It gives an indicative value, and you, by your own judgment, you can refer to other references also and then correct it also. But then that is what a practice engineer who wrote a book gives us basically. So today we don't have to conduct again a plate load test for getting the modulus value, because the basic fact that again the same problem comes in. We are only getting the soil just below that only, below the small plate is effective depth, but those are influence now. So that values which are going to get because of all the limitations are going to be, I mean, in my loose words, not worth the conducted test now. So there are methods which are all provided by the code also, but I have skipped deliberately. So don't think that I have just done by inadvertently, but deliberately. Most of us believe that it is outdated test. That's why, though the provision exists now, I focused upon other forms of testing. Okay, and also CPT I didn't give much importance because CPT is something used in piles. It is a must for us to use in for piles and clays, and hopefully when the defoundations are done, more importance and more ways of testing also are going to be included in that now. So with that starting point now, the code actually gives us different steps of doing it. I will just quickly summarize them only, and all these are, as I mentioned, extract from the code itself so that we don't get confused with the wording now. So we are divided into two steps basically. One is the cohesionless soils and another is cohesive soils. So one is that we are talking of soils with cohesion and angular friction resistance. Now, can I ask you, what are the soils with cohesion and angular friction resistance? One, of course, as most people report in the Union report, the so-called traction value of getting CN5. Now, this for half the time, I somehow believe that these values which are going to get CN5 by UC test or by U test are going to be beginning with a saturated soil sample below water table, and then the sample got dried out on the way, and then of course we got basically a cohesion intercept as well as phi now. So that is not the C5 soil. Okay, the other kind of this one is if you are conducting a test on compacted soil on which we don't normally build buildings, this is going to be again not correct because unsaturated soil. So in the first case, it was a saturated soil. We converted by our carelessness into unsaturated soil. Desiccated got desiccated, and so all the problems keep coming up. Then when is the soil really going to get these values? Is going to be only for obviously for a over-consolidated soil. Today we'll also see what exactly over-consolidated soil again. We'll just recap maybe our concepts now and see that now. So this particular clause, it says very nicely. It doesn't say effective or something like that, but then it is silent on that. So let us grin and bear it. So soils is both C and phi. to calculate the UBC. Hello? Calculate the ultimate net bearing capacity. We have the same equation which you thought of now. And in case of local state failure, we already know what is the way in which we have to do. So it refers to the table, and the table gives us these values. Basically, strictly speaking, I don't know where from they picked up these values, but anyway, this is what is given by the code. We will follow these values, and I have described also for phi is equal to 30, it is 30.14 and 18.4 and 22.4, and at 35 it becomes 46, double this value, and here also almost double now. So what is it you find is that the change in the factors of bearing capacity is so humongous when you increase the values of phi. That means our testing has to be nearly perfect. Then, of course, for understanding the local shear conditions, it always says, we already mentioned this now, the modified value of phi we are going to take will be tan inverse 2/3 tan phi, and also that as usual, we are going to use the 2/3 of C also in that equation. So that is the basis initially specified by the code. Then they say that was for stiff footing. It doesn't say there, but that was for stiff footing. And now for this, we are going to modify for the shape, for inclination, and the depth of embedment. Mind you, these are the words which are used by others, particularly Hansen now, and effective order table, which is also implied in discussions on the basic bearing capacity equation. So the shape of the footing, inclination of the loading, and depth of embedment are considered now as the factors I have to mention now. Factors of shape, depth, and inclination for C and C component, and again for the surcharge component also we got SQ, DQ, and IQ, and for the B gamma and component also we got shape factors and English factors and the factors of S gamma, N gamma, S gamma, I gamma, and things like this, and local shape value in the same way as we are going to do it now. So in this now, I think I have already focused attention, but it is worth really looking at the same application of the same equation in many different ways. What is the different ways now? We know that the factors, bearing factors, NC and gamma and Q are functions of phi only. Okay, the theory could be different in choosing the shape of the shape value zone and then also saying this is going to go into such a zone or not. These are all there. But each theory gives us basically the bearing factors, NC and gamma and Q. Clear now. So that means phi value is going to be very important. Then from the solve viewpoint, the unit weight is important. The unit weight means density, what you call now, is very important. So what we are going to do, we already seen the last time also. If depending upon the placement upon on the water table which are going to encounter in the service time of the structure now, we are going to pick up a water table condition, the worst condition we can think of, and then of course carry out further implications of water table correction in this now. So that is done for the gamma. Then what else is there for us now? The other two factors which are going to be influencing the bearing capacity is going to be the depth of the foundation and obviously the width of the foundation. So it is very clear that the width influences one of the most important parameters. B is influencing this now, is in this parameter now. So higher the width now, higher will be the unit bearing capacity. Mind you, we are going to multiply tomorrow by the actual width anyway. But calculating the actual load bearing capacity, we are going to find out what is the influence of this value multiplied by the B. So that means B is going to come twice. One the equation and one is going to be the actual calculation of load bearing capacity for that width. So B, the width of the foundation is going to be very important. Then of course depth is important from surcharge now. So deeper the depth, it's going to be good for us. But then let us see for clays what is going to happen. And for there are conditions which we are going to see now, and which we have to use this very carefully in defining what we call as the net ultimate bearing capacity. And so the C value influences essentially this component only. So we have to go back and give assignment to our students now. What is the influence of C and phi on the bearing capacity values which are going to get now? What is the influence of water table changing from top to bottom? Tomorrow we'll also see what is the influence of water table change basically in terms of settlement or consolidation also. And then we're also going to see the influence of course, just gamma we already said on effective unit weight, sum unit weight, and then also effect of other things, that is depth of foundation, width of foundation. What is the factor which is going to influence most is what we have to see for a given status certification. So this kind of assessment we can get it done through students and let them understand what is it which is going to be very critical now. So they have given the shape factors, they are given for stiff footing, rectangular fitting, square fitting, and circular fitting now. And B is diameter in the bearing capacity formula. That means it's got the total width only. Okay, so shape factors are given here, C, SQ, and S gamma. For all these four shapes, they have given the shape factors, and then also the depth factors are given now. Okay, so this is something which are also going to take depth factors again for cohesion, for surcharge, and for the basic gamma kind of function, integrated kind of function. Then we got the inclination factors also defined. The two factors are same, only one I gamma is different. IC and IQ are really going to be same. So also, what is it we find? That by and large, again, they are functions of phi only. That is something we have to always keep in mind. They are the function of phi or functions in the case of shape factor, functions of B over L now. So that is what we have to see. B is breadth and or width, and L is the length of the foundation. So these are the, I mean, we are always playing with these values only of the fundamental solid properties of the fundamental foundation parameters which we are choosing. So that's why the determination of capacity is an iterative system now. Because nobody is going to say that in assignment only we say calculate for this width and for this depth what is the bearing capacity. No, here it's not like that. Here we have to choose the parameters and then do that. Means we determine now what is the most convenient depth and what is most convenient or economical width also. If you are going to choose a shallow foundation with a narrow, I mean with a smaller depth now of the foundation, naturally the width could be sometimes very large, and so the foundation might touch each other now, almost nearly touch each other. Or if you don't calculate properly, obviously they may even overlap also, at least hypothetically on paper now. So that means the determination of this depends upon the column spacing we are going to have, or placement of intersection structures like a wall foundation, something like that now. So this is something, it is ultimately an iterative process where we are going to get the result now. So again, like these all properties are not unique, it depends on the conditions. Here also, the so-called bearing capacity values are not unique in that sense. They are unique in depth and the foundation. So how the recommendation is made in many geological reports, we don't even know how the recommendation is made. They just calculate one value, assume some parameters and do it now. So that is why it leads to confusion. So for the table I mentioned now, exactly same fundamentals are given. So I'm not going to go on to that. So the second stage of the code is going to be only for sands. So for sands now, what is it they're going to say? It depends upon the relative density of the sand basically, and relative density range is given. And here, what is they're trying to say? The void ratio is going to be, I mean, for relative density greater than 20% or greater than 20%, or void ratio less than, I think, 0.55, and then it is taken as dense condition, and then the method analysis is going to be general shear failure. Okay, now less than 20%, of course, the values are going to be, the void ratio is going to be 0.75, more than 0.75. The condition of the soil is loose, and then only local shear. As I said, local shear and bending shear are put together now. So very clearly, for relative density more than 70%, for void ratio less than 0.55, the methodology you are going to pick up is general shear. And for less than 20% relative density, which is really not going to be happening most of the time, and void ratio is less than greater than 0.75, it is taken a loose condition and we will local shear failure. If the values of relative density are going to be between 20 and 20%, if the void ratio is going to be between 0.55 to 0.75, we take as medium condition and then we have to interpolation. That means we have to do the extreme values and then linearly interpolate, not extrapolate, interpolate now. Now this is something we have been doing anyway, but then the point which I am going to mention is we have to get the correct relative density of this now. Okay, we determine this value. It's not so easy for determine because we are going to put one or expected values to begin with now, and that itself is highly questionable now. So that is what we will say this one. So then we have based upon the next way. First is we got the value of relative density and everything else. We got the values of void ratio. Now he says directly we can use the SPT itself. So for the SPT itself now, obviously the equation which are going to govern is going to be not inclusive of the C parameter because this question solves absolutely no zero at all. But then we should also see that we are going to consider This is mentioned earlier also. If you just want to read this now, the SPD shall be determined as per whatever it is at every 25 centimeters, and then in the vertical direction, and of course change of state also if it takes place earlier than that now. So we are going to consider the average value beneath each point shall be determined between the level of the base of the footing and the depth equal to 1.52 times. This always is keep saying it 1.52. I've shown you the F value, how it's going to happen now. I've shown you how the depth of impulse is going to be there. So from all that now they surmise that the depth of impulse is going to be 1.52. So we are considering an assumed value of the foundation, and below that 1.2 times that of the width of the foundation as the effective zone of influence. And these values of SPD or N values are taken actually individual values, and then if the individual values are more than 50% greater, then the average it shall be neglected. That means the individual value can be neglected, but then don't neglect the smaller values now. That means any value which is higher we neglect it, but lower we don't neglect it. In fact, I keep doing this every horizontal level. That means we have a number of boreholes now on a given profile, and I first draw a horizontal line on that now at a given depth. I find out what is the least and what is the best now, and find out an average of that, and then go to the next depth now. That means it's not done only for one borehole, because we can't take a decision on one borehole. We have to have a number of boreholes, and from that you draw some typical cross sections of profiles, and from that profile now you assume a horizontal plane. Let us say in the horizontal plane now, what are the SPD values are going to be there? Correct SPD values. Sometimes you don't correct also, you just leave it like that only. And then what we do is that we try to take again the average of all of them now, neglecting values which are very high and not neglecting values which are loose now, take an average of that. So that is average value of the same strata for a given depth now. You keep going down further, and after all of them are achieved, then again you take an average to get one single value. So that means all this is going to involve the choice of design parameters. Design parameter of SPD value is not so easily done. It's just not based upon one SPD test. It's based upon number of tests now, and a lot of averaging is done now. From that, of course, I mentioned corrections are done now. And if everything is done, basically, we use the same equation as recommended earlier, except the C component now. And what is it which I said is that we use the same shape and depth factors. There are no cohesion there. Whatever correction is going to be the same only. And only phi value, we are going to take it from the table, from the graph now. So I have just put it in both directions now. So again, they have given us the very loose condition, medium condition, dry, we've got dense condition, very dense condition, and SPD value versus this now. And for when once you know the SPD value, that means if you know the SPD value, we can predict what is the angle now. So that is the prediction which we are going to give. And mind you, for very loose soil, that means beginning of medium soil now, the angle is 30 degrees. What is the value of SPD at that time? It is 10 only. SPD 10, that value is going to give you 30 degrees now. So SPD 30, let us say, is going to give us the angle of 36. So that is the correlation they have maintained, and this is what I have followed if you are going to use this code. So we have got the earlier relative density, if you are able to get it now, and then we also thought of comparing with the white ratio values. Now we are able to use directly the N value, and then from that the chart which is giving you the angle friction, and from that we do the calculations exactly the same way as we are doing in a standard way. So then we got for coastal soils. For coastal soils is very simple anyway. So we got only one parameter. We know that it's undrained values, mind you, the net admitted capacity immediately after the construction on fairly saturated homogeneous coastal soils. I don't know what you mean, fairly saturated, shall be calculated from following formula. So that is going to be C and C anyway is there, and then the factors for shape, depth, and inclination, and this is there. And I have mentioned also some people take it as 5.14 Tazagi, and then other people take a 5.7, some people take 5.9. But anyway, it is a very low value of NC, and which you are going to take the correction. So the point is that if it is going to be on a clay which is saturated, I will say that not fairly, it's saturated, then we are going to do the undrained test, and then we are going to use the C value, and rest of it is going to be same. So NC is the only thing. NC is again constant for this particular method, but then we are going to see for layered soils what is we are going to do. So this is for equation is meant for fairly saturated material. Now, when once you place the foundation, naturally it is going to stay there with the loading. At least most of the loading which are going to building load which is permanent and which is semi-permanent. We know how to take the loads for design of structures, and so that load is now going to be permanent now. So when that load is going to be permanent now, we know we will calculate settlement later. But then the point is that when one settlement is there now, what is going to happen now? It is going to be consolidated soil now. Consolidated soil is going to improve. It is actually densifying the original soil now. So we have to really find out if you want to assess the long-term stability of foundation. Now we will have to get the naturally behave, take it like a normally consolidated clay now. So what is the effect of this consolidation is what we are going to infer. And from the standard test, like we said, triaxial, we can infer now what is the effective cohesion, that is C phi, C prime, and effective angle of friction phi prime, and then use those values, incorporate them in the same original equation we had for C phi soils, and then get the long-term bearing capacity. Now, common sense will say that that's always going to be better because it's no consolidated soil now. It has got improved C prime and phi prime. Here we are talking of just after construction only. That means the soil as it exists actually. So, mind you, we are doing the total stress method for this now. For long term, we are going to do the effective stress method now. Now, we rarely do that the second analysis because of the fact that, oh, anyway, it's better soil now. When once it is taken initially, it will take now. But then we have to also see basically what is the time of construction? How long is the construction going to take place? Is it going to be very slow? If it is going to be very slow, the construction is going to occur now. And further improvement, of course, we do by other methods also, by using sand drains or whatever it is now. We can also improve the soil. So if the soil is very, very soft now, mindly applying this and then say that my bearing capacity is very low, I do something is not sufficient, I do something more than just calculation like this. I have to see what is the long-term effect of the situation, and then is it possible to improve this bearing capacity is something we have to keep in mind. The second thing is that he also mentioned very clearly that we have to consider the values from UCS. We already mentioned this, how to get the C value, and then the factors, of course, shape and depth and inclination are obtained from the table, like I already shown you. And then we have got the shear strength for a depth of 2/3 B beneath the foundation does not depart from the average by more than 50%. That means we are considering now the depth of inclination as 2/3 B only. And if we got number of values now, we are going to look at the average of that now. If a single value is going to be more than 50% of the deviation, then naturally we will have to use the average. If it is not so, we will have to consider as a layered material. So they give us a solution for two-layer solution, which you will see very clearly. So the point we are trying to say is that now that we will have to do number of tests now. What do you mean by foundation does not depart from the average by more? 2/3 B we are considering. In a depth of 2/3 B, we are going to have number of points now. How many points we are going to have actually? We are trying to say that we are doing SPT at every 0.75 meters. And when once we finish one test now, we are going to naturally make the borehole deeper now by another 30 centimeters, by another 75 centimeters. And before that now, I mentioned earlier also right in the beginning that we need to take undisturbed sample. And so number of undisturbed samples are taken now, and correction and testing of them has to be done to be able to get these values. Isn't it? So normally if you go by the standard alone, we always get confused because we don't have so many values to say that. We just have one value only to do this. So then how we are going to say all the average business? So indirectly by saying that I'm going to consider the average and deviation from the average, obviously it means that if you know there's clay soil, we will have to take out number of specimens and then get the testing done and not SPT. This is a point our good friend from Assam was mentioning actually, that for clay soil, naturally, it's always possible for us to take this because the influence is defined in the code now. And we need values, number of values of the C to be able to decide what is the design value which are going to put in the equation. That's number one. So then if occasion demands, we may also consider the two-layer system. Multi-layer system we can't do in this code. We can only do by FEM or some other methods now. But then we are considering only two layers as C1 and C2. That means top soil has got a C1 value of C, and then bottom soil has got C2. Only two layered, and we are assuming that these two layers are going to rest ultimately on a stiffer soil. So for this now, this particular code gives us basically a chart if I believe strongly, then this is actually the chart provided, developed by Professor Reddy, A. Siva Reddy, and Professor Raja Srinivasan. So this chart was also given in the earlier editions of bowls, but I think now I find that it's not there. But anyway, they adopted that from Reddy and Srinivasan work now for two red soils. The only thing we have to remember is that, which also mentioned in the amendment to this particular factor is not C1 by C2, it's actually C2 by C1. This please, if you did note it, please note it now. So this particular value is C2 by C1. So what is it we are trying to say is that if the depending upon the kind of soil we are going to have, which is going to be stronger. For example, C2 by C1 are less than 1. What it means? The C1 is stronger, is it not? C2 by C1 less than 1 means C1 is stronger. C1 is good higher. So we find that this value of NC we are going to use is going to be less than 5.14. On the other way around, it is going to be different when the exceeds is going to be there, and then of course it's going to be higher than. But mind you, this limit is again around 9 or 10 only. So the change is always between 5.14 and higher. So that is what we have to see how this thin soil or thick soil of soft soil in the 2 days is going to influence the overall behavior. So then of course eccentricity can be considered. Again, how to consider eccentricity is not mentioned in the earlier codes now, but this is standard practice we do in our structures also. So eccentricity can be one way or two way. If you talk of eccentricity from the length direction now, the effective length is going to be considered. That means from the point of propagation of the load actually from the center of gravity, naturally that is the distance is taken as EL. That means eccentricity in the longitudinal direction now. So L minus 2 EL is going to be the effective length of the foundation for bearing capacity, for load bearing capacity. And then width also in the same way, eccentricity in the width direction is considered B minus 2. So that means instead of using B in the equation now for bearing capacity, we are now going to use B prime. In the area calculation, please remember that we are going to use both corrected L and corrected B. So which is going to influence the total load bearing capacity, the foundation, based on the equation now. So when we try to do that now, what is it we are trying to say? That is the actual width and length of the foundation is going to be L and B. For calculation purposes, the bearing capacity, we are going to use the reduced width or corrected width, corrected by twice the eccentricity. And length also we are going to do it by again correcting it by twice eccentricity. And the total area is corrected now as the corrected length multiplied by the corrected width now. So this is going to reduce the effectivity of everything. Now, this comes to picture particularly really eccentric loads, and also sometimes we have structures abetting the neighborhood structures. So wherein the column, your foundation is going to be just touching your property line. So in those cases, it's going to come now, but it's not very common because we are going to spend more money in actually constructing the full length and full width of the foundation, which is a waste actually. In terms of contact, it's going to waste only. So we'll have to take this into account also. This is mentioned right in the beginning of this itself. So then, of course, I'm referring back to the beginning of this code actually. In this code, what they are trying to say, they're trying to say that the definitions are given now. They call net loading intensity, ultimate bearing capacity, safe bearing capacity, safe bearing pressure, or net solid pressure for specified settlement, and then allowable bearing capacity. So if you look at the terminology now, allowable bearing capacity means now the net intensity of loading which the foundation will carry without undergoing settlement in excess of permissible value for the structure under consideration, but not exceeding net bearing capacity. So what is it which is trying to do? One is that it will not be more than net bearing capacity, net safe bearing capacity, and then it will be able to, it will not settle more than the permissible value. So only thing is, we said probably if you use a word called pressure, it will be better because capacity always means, people don't read this entirely in its entirety, and they say that bearing capacity means bearing capacity, and safe and allowable means same thing. So that causes a bit confusion. So for our kind of terminology, we use basically, at least ideally, we used to use the allowable solid pressure so that there's no confusion on this one. Okay, so though this the terminology is confusing now, but the most important point is that before giving the recommendation on the so-called load bearing capacity of the foundation, now for a given width and given for depth of foundation, the load it can carry is given by the term allowable bearing pressure. But then we should also see how that particular gentleman had defined these values, whether he referred the terminology by the IS code or not, is what we have to clearly see. So then, of course, this is what also is said, bearing pressure, many things now. So we are considering basically that the next phase of this entire foundation design from soil viewpoint is going to be considering both these factors. That is also mentioned clearly, and that makes us move to the next aspect, most important aspect of the settlement. Because in taking up the load now, any load which are going to be on soil, it will definitely cause settlement. Sometimes the settlement is instantaneous, sometimes the settlement partly occurs immediately, and also takes time for the total settlement to occur. So that is what we are going to have a look at that. So if you look at the total behavior now, which we are going to go through in detail now, for sand, sometimes you find that the settlement is going to go on. It looks very silly. Sand is very strong now, and so usually problem of bearing capacity doesn't arise now. And even if it is sort of loose now, the moment you construct the foundation, naturally settlement now. If the settlement is going to be occurring during construction, then we're very happy. So that is why the settlement governs usually, but then what's happening is the settlement is occurring during construction. So we're not worried so much about that. So there are a lot of theories which are going to see one of them. We are using elastic theories only, and that's why the settlement code also gives us how to calculate this now, but then people don't really give much importance to this unless the soil is very loose, unless, the sand is very loose, or very important structures like nuclear structures, things like that only, we are going to give much importance. Otherwise, we just sort of ignore only. Then for the clay soils now, it depends upon both bearing capacity and settlement, and we will not say it is governed by the bearing capacity, governed by settlement, because both are going to be equally critical. So that is what we are going to consider. So what is it we are going to look at? Basic criteria will be that we need a sufficient factor of safety, and we need no excess settlement, and also we do not allow any different settlement. It should be under control. So that means what is it we are going to say? We are going to say that not only is total settlement of the structure of the foundation, and then also we are going to bother about the different settlement between the adjacent footings or adjacent foundations. We have to look into both these aspects. So that is the criteria, and we are going to come to this aspect of settlement in the next step now. So I'm calling it now assessment of settlement. Assessment of settlement sometimes looks very easy and sometimes really complicated. And if some of you have occasion to read through the smaller books which are written by Simons and Menzies actually from the Imperial College, you will really get confused because he actually gives us a lot of data to show that the settlement you have calculated by any means, any method, basically can be off by more than 100%, maybe 200%. It can be above, or it can be below these values. And that means it will be plus or minus calculated settlement now by the best methods. So sometimes we have, we can finally say that then why we are bothered about settlement. So that is also what we are going to discuss in detail. But the point is that in case of critical structures, we will have to also monitor the settlement. Okay, that becomes equally important. So when you talk of settlement now, we are talking of settlement which is going to be non-recoverable. Obviously, the structure is going to be there, so the settlement it could be elastic or otherwise, or naturally, that is non-recoverable kind of thing. Then, of course, the other settlement which is going to come out is it is for saturated soils, and it is going to be time dependent. Okay, these are the two things which are going to always keep in mind, and somehow that inadvertently we are doing things without sometimes realizing what is the importance of this. And this is clearly shown by a small, you can say, funny thing mentioned in our famous book by Lyman Whitman. And what is said is that for the Tower of Pisa now, the engineers then those days, the so-called field engineers, they say that I skimmed a little bit on the foundation, but no one will ever know the difference. Because the structure which are considered the foundation structure is not visible to anybody at all. It is the main structure, the superstructure is visible now. So unfortunately, nobody did anything, but the kind of soils which are there below this present leaning tower are something which they didn't anticipate. So that's why the tilt has occurred. So We can't say that I skimmed a bit of it here and there, I reduced the width or reduced the depth and I did something. Finally, it will cover up, but it will show up on the main structure. And if it is showing a main structure, obviously, it's difficult to rectify also. Very difficult and very expensive to rectify that also. And if you read the literature, so much literature available on leading to Oropesa, the history of it now, what kind of soils, what they do, how many so many commissions. Very interesting data is available, freely downloadable on the internet. We should see that now. So what we are looking at is not only the tilt which happened. If the tilt is going to more naturally, the structure is unstable, and we're also looking at the settlement, the total settlement, and naturally also any small tilt is going to also cause cracks. And we will see the typical structures. This is the same Tower of Pisa. And then this is the Palace of Fine Arts. We'll discuss it towards the end of the presentation. Not today, maybe next presentation. We'll see that this is one structure which is settled by more than 4.5 meters in 100 years. Now, if you look at the total structure, nothing happened to the structure. Structure is intact basically. It was simply settling continuously every year. Now, it's the Palace of Fine Arts, one of the fantastic structures they built in Mexico, designed in 1904 and probably finished in 1930 because of many situations now. And even now, it is worth really look. It seems if you see from the net, you will find most of the historical structures, historical paintings, and other things are really there, and it's worth seeing for the tourist spot. But then, what is happening is, after all, this has got a facade, which we'll see again at the end. And the entire facade has gone down by one floor, basically, 4.5 meters. So, what is the look we are going to have now? Where they are going to take your cables, where your water line connections there, where your sewer connections there. So, earlier people were walking up to go to the porch. Now they are walking down actually to get to the porch. Can you imagine now? So, we'll talk more on this at the end. So, basically, what we give importance is not necessarily the initial elastic or light settlement. We talk of the time rate at which the settlement occurs, and that is because of the basic fact of consolidation. So consolidation causes settlement. So the way in which we look at it is consolidation in saturated low permeability soils under external loading is about building up the effective vertical stress by dissipating the initial excess water pressure in the soil through drainage. There's many things now. That means once you load the soil by constructing foundation, it will develop naturally excess pore water pressures. So these pore pressures are going to be slowly dissipated depending upon drainage conditions available now, and that will build up, increase the effective vertical stress, and by which process, obviously, we have just mentioned this, the strength also improves. So in a way, it is good, but it is going to taking time now. It depends on the load also. It depends on the permanence of the load now, and we also require drainage conditions. We got the drainage capacity, what you call permeability of the soil we are concerned. But then where the water is going to go out, that means where the excess pressure is going to be dissipated, we require a drainage layer also. So this something is there. So what is it we are going to do is that whatever excess load we have applied by the foundation now has to become effective. So the time taken for this is ultimately is what we are going to do. So that means the excess pressure is going to dissipate, it becomes zero, and so all the loads, that means the entire vertical stress is going to become effective stress. That is what is going to be the basis now. It is good for us, but it causes its own this also. So it is a long-term response of that now. So as I said, this particular structure in Mexico has been settling for 100 years. In fact, many structures, the entire city keeps settling because that's the kind of soil they are there now. The soil will drain over months, maybe years, maybe decades, maybe centuries. What is causing now? It is causing reduction in the void ratio. It is of course causing settlement because of this now. And the most important point is that the amount of water which is going to get out, the total quantum of water, the volume of water which is going to get out, is going to be the change in volume of the soil. This is what we have to always remember because we are dealing with the saturated soil now. If X amount of water gets out now, so that much amount of volume change is going to occur in the soil now. That's why the water ratio change is occurring. That's why the effective stress is increasing. That's why the strength is increasing. And so for this consolidation now, one type of consolidation, for such a simple situation, we are looking at the volume of water only. We are looking at the volume of water simply. We are going to define this in this case. How do we mean one type of consolidation? That means consolidation occurring only in one direction now. If you remember Terzaghi's theory now, one of the main assumptions is that it is consolidation one time. That means the flow is in one direction only. Okay, and the sediment also in one direction only. But if you really pick up a saturated soil now, though we don't recognize it now, there will be lateral movement also. There will be also lateral flow. The lateral flow, in fact, for a natural clay deposit now, the permeability in the lateral direction, horizontal direction, is going to be more than the vertical direction. Mind you, we are not considering all of it now because we are taking a specimen of sample from our sampler. We are studying from the sampler, taking a small sample and putting in the consolidometer or odometer. When we are putting it like this now, we are putting more or less the horizontal layers only. We are not measuring what is happening across the specimen now. We are measuring only vertical direction only. So we should remember that it is very critical for us to realize that there is definitely a 3D flow and 3D consolidation. The first impact of that is, of course, realizing that this calculation is incomplete or not correct also. It has got a lot of variations with respect to the initial access forward pressures or forward pressure, and then the drainage condition at the top and bottom of this, not only in the specimen we are having, but also in the field now. So we give a lot of importance to this, but there are, I think, 7 or 9 assumptions. If you see classical books on soil mechanics, we find there are a lot of assumptions there, but assumptions which are most important is, other than isotropic, homogeneous, elastic, all those things. Now, what is it we are trying to look at is, we have considered in our studies in the laboratory one-dimensional flow and one-dimensional settlement or one-dimensional consolidation, we call it now. But in real condition, there is definitely a flow in the lateral direction, in the horizontal direction, and also there will be lateral movement also, soil also, at least in the beginning, when this excess power pressure is going to be generated. So this, what we are assessing, is a simplistic case. I will also repeat to tell you that the K horizontal, the permeability horizontal direction, is more or less likely to be more than the K vertical. Now, how come we are doing it? Because there are no drainage media around. So that's why the flow happens to be in the vertical direction only. So from this concept only, we arrived at sand drains, we arrived at PVDs to make use of this facility of higher drainage or higher permeability in that direction. We effectively use it in constructing a sand drain or a prefab vertical drain to see that the consolidation is going to occur quickly before we construct the foundation. So mind you, this is a basic fundamental we should always remember, and not from examination viewpoint, from the practice viewpoint. So then, of course, we have said already that once consolidated, soil is better. Okay, less void space, greater contact with soil particles, and then, of course, it's always stronger and stiffer. More juice is more. So if you look at that now, the epsilon value is the strain. The strain which you are considering, that means the change in thickness or the main thickness or the total thickness is going to be equal to the change in void ratio divided by the 1 plus initial void ratio. So what is this now? This is a strain condition, change in void ratio or 1 plus E naught. That E plus means initial void ratio. So what is the strain now? The strain is equivalent to change in height, delta H by H. Or we can call it as delta V by V. So what is it we are going to get is now, without getting into any other thing, by just having the so-called void ratio with the pressure conditions now, for the change expected in the consolidation pressure or overburden pressure now, we just measure the change in the void ratio and we can directly expect the change in the height. That means delta H is going to be the change in height, means the settlement now. So we just need this basic equation only. Later we're going to express in different terms like MV, AV, CC. They're all ways of expressing this relationship only. Okay. And then it also looks for changes in this E log P curve or EP curve, which we are going to consider. So if it is so long is a straight line, basically, this is going to be simple. And in fact, it takes care of many issues. I will come back to this at the end of the presentation, not today, but the next presentation, and see how important it is. So what is it we are going to do? We are going to pick up a soil sample, place it in a consolidometer ring, and we got drainage media. That means we got a porous stone, and between these two we put a filter paper, and then start loading basically after filling the entire thing with the container, and after saturating the porous stones also, we assemble it in a consolidometer gang. You can say that number of specimens can be done there. And the point we are trying to apply a load and measure the displacement. Earlier we used to measure by L gauges. Today we got a lot of LVDTs because they automatically give you that you don't have to stand there, start a stopwatch and things like this. So through LVDT, we can automatically get a continuous measure of this now. So in trying to do this test, we are not going to describe the whole test now. What is it we are really going to do? Apply a load or apply a pressure, apply stress on the specimen and measure the change in thickness by the so-called displacement vane device with respect to time. So when once there no more change now, that means the end of consolidation, further better load now, we are going to apply the next increment of load now. So there is a load increment is happening now, and also there is a time lapse we are going to have. You apply a load, we know that there is a, when once you apply a load now on this, there is a excess forward pressure generation. And slowly, depending on the thickness of this, depending upon the drainage zones on both up and bottom, top and bottom, it is going to take time for consolidation to occur now, or for the excess forward pressure to be dissipated, and that is a time, that is a question of time and phenomena, and that is what we are going to note in the laboratory by actual measurement. So when no more change is there, we are going to apply the next one now. So we are going to apply different load increments, and for each load increment, we are going to measure the time versus the change in compression or change in the dare gauge reading now. So this is what we are going to do. So we are going to apply some loads, and we are going to obviously ultimately come back to no load condition. So we are going to apply a load cycle. We are going to get back a unloading cycle, a loading cycle, unloading cycle now. Now there are many ways of trying to do it. It's not only always loading and unloading. There are better methods of finding out other behavior now. So what is it we are going to get now? We are going to get now these charts in many different ways. So what we are going to do is that we can think of what is happening in the middle of this forward pressure business now. At the intermediate level, it is still going to have some pore pressure, excess pore pressure, and the end of that load increment now, the pore pressure is going to be zero, and this is going to be there from beginning to end at the drainage surfaces anytime, because near the top and bottom of the sample now, we got a filter paper, we got the porous stones now. So the pore pressure may be instantaneously developed now, but it will be instantaneously also becoming zero at the drainage surfaces. So then soil drains from the middle of the specimen to the top or bottom of that, and naturally we are bothered about from the middle of the specimen to the top or bottom. If there are porous stones on both sides, imagine a case wherein there are no porous stones on one side now. So the path of movement of this is going to be the entire depth of the specimen, entire thickness of specimen now. So then the path length is going to be full value of thickness. If it's going to be having porous on both sides, it's going to be half the thickness. So that is going to be there. So for each stage I mentioned, there is a time rate of consolidation. At all loading stages, if you take the values now, we get the so-called compressibility of the soil. We also know the consolidation history of this. What happened, the stress history of this. And if a stress history is not known to us earlier, we should look for, was there any pre-consolidation? So that is also what we are going to get out of this system. And then, always I told you, there are cases when we are going to construct the foundation or take a specimen also. What we are going to do? We are going to take a specimen at 5 meters depth. We have to remove the soil of the top 5 meter soil. That means we are unloading the soil. And then we are taking a specimen now. So when once you take the specimen out now, it was existing under an effective overburden pressure in the field of 5 meters, and now it became zero. And now we are going to reload it now. The same thing happened in the field also. When we construct a foundation now, what's going to happen now? We are going to, let us say, if the foundation is going to be 2 meter depth now, we are first going to remove the 2 meter thickness of soil now. So we are going to remove that overburden now. And if water is there, water level is high, naturally water is also going to come and fill up this. And for example, there's a problem in the weather or there's a problem with the contractor now, he didn't contract, let us say. So what's going to happen now? The soil, which is supposed to be at the foundation depth now, is also going to heave. It's going to swell, it's going to rebound. Because earlier is a 2 meter overburden now. So now we remove the overburden, eroded to happen, naturally whatever happens now. So the entire specimen is going to have a concave upwards kind of phenomenon. So when you really start considering after a few months or whatever after contact is a problem solved, so then it is going to consolidate now again. So that settlement we didn't consider earlier, because this consolidation occurring because of the rebound of swelling which happened because you didn't construct the foundation immediately after excavation. Immediately after excavation, probably there could be some rebound, but you allowed this to happen. So the water slowly moved around, and naturally it gave a rebound. So this is something we have to remember from practicing point also. So in which case now we are going to get settlement much more than what we anticipated, what we calculated by the normal test now. So that is something we have to keep in mind. So then we are going to get two parameters I mentioned, two such parameters. One parameter is going to coming out by the rate of loading, not by the rate of dissipation pore pressure. So we have a parameter called CV, coefficient of consolidation, and fundamentally, the theory gives us that it is related to the permeability and then the value of the compression behavior, and also the parameter representing the MV, and then of course unit weight of water. So we can get these values, actually get the value of CV by using a graph between the settlement or compression with the square root of time or log root of time now. And this actually is again an empirical procedure. Okay, in fact, Sridharan himself has developed a new theory of plotting hyperbolic plots and getting this value also. So there is no scientific about this, but then we follow for most soils a root T method, and for some soils which are generally soft and which consolidate more, which are subject to even secondary settlements, we use a log turn kind of procedure. So uh, in these procedures, what is it we are trying to do? We are actually trying to plot the root of time on this axis, on the horizontal axis, and the compression as observed by the dial gauge on the vertical axis. Okay. On that plot, we can plot the log of time, log done this one, and then compression here now. So from these curves which are going to get now, these dots are going to represent that now, we manipulate. How we are going to manipulate? Theoretically, we find that if you plot in this fashion, the theoretical line is going to be a straight line actually. So by using the straight line now, we can predict what is the time interval which is taken for 90% consolidation. Okay, so that is what we are trying to do. In this case, you know very well how to do all the things now, and the master students would know automatically that we extend the straight line portion and it cuts here into the origin, and the difference between the initial reading and this extension of the straight line is going to give us the initial compression, and then this point at which is cut is 90% consolidation. So at 90% consolidation, we can find out the value of T, capital T, uh, we are going to get, and UV, you can get it, 90% U. And from this, by manipulating this appropriately, what is it we are trying to do? After doing this, we are also going to draw a line which is 1.15 times the slope of this line. And wherever it cuts only, we are taking this as T90, time for 90% consolidation, actual time for 90% consolidation. So which you use in the time factor. This equation given by Razak is so that we can get the
Sir, your voice is not coming. So, dear participants, Professor G.V. Rao sir is again joining. Some issue at his end. Please wait. If you have any clarifications, you can interact with him. Hello. Yes, sir. Hello, dear participants. Professor G.V. Rao sir has just called me. He has the network issue. So he said we'll stop here. And again, one more lecture of his is there on 4th February. So during that lecture, he will cover the complete settlement analysis and whatever remaining part that is pending. He was about to discuss about coefficient of consolidation and all. So this he will continue and then complete settlement analysis of footings in Cojo soils, cohesionless soils. And after that, he will also discuss about permissible settlements for different types of foundations in different soils as per IS code and other codes. So I once again thank you all for participating in the forenoon session of this faculty development program. So attendance sheet is already posted, link is posted in chat box. So just kindly fill in before you leave the session. And again join back at 3:30 for a lecture on RAP Foundation by Dr. Nilma Sachima of IIT Indore. Thank you all. Have a good day.